Started?
Okay, yes, let's start.
Okay, great. Let's start the other. Okay, I have good news and grave news. Oh, it still worked. Okay, so I start again this. Yeah, okay. Great. I started this record and now I start the class. Lecture PDF. Yes. Great. New week, new hopes. I have news. Yes. As you could see, I uploaded the course material to Moodle, YouTube, GitHub, everywhere. That's a good idea. I have to. Oh, no, I can't. Doesn't matter. Perhaps it's no one will go. I don't really like the style of this class. It's not up to me what I tell you. I talked to Professor Erwin Ratz, who is responsible for this class, for this lecture, and he told me, yes, this is it. I just tell you the important things. Well, this is not the way how mathematics or physics are taught, so this is not my way, but I have to do it. At least you will have homework, you will have exercises, good exercises, and you will practice. But this is, so there are requirements from us and from you. You will be electrical engineers, so you must understand the waves, oscillations and everything. And that's very, very important. And this is the main point of this class, at least the mechanical stuff. You will also work with mechanical engines, so you must know the thermodynamics. And also you are electrical engineering, but the electrical engineers, at least the Hungarians, do not know what is electric potential when they start the electric engineering, the professional subjects. So I must tell you everything in one semester, because you can do it. You can understand everything. Yeah, this is like in the joke that someone asked how much time does it need to learn Chinese. Chinese say, okay, 1 year. Language teacher, yeah, you need 3 months. University student, do you have notes? Yes, okay, for tomorrow I will prepare. That's something like this, this happened, but they will change this. Some of you told me you had a physics preparation, physics 0 course. And you have this course, physics 1 and physics 2. These courses will merge, and you will learn mechanics, thermodynamics, electrodynamics, and modern physics. The problem is that was 4, and it's still 3 semesters, so good luck. So it's better if you pass right now. Okay, good news, number 1, I will start working in Strasbourg 2 weeks later. I haven't seen my contract. They told me my contract will be delayed 2 weeks, and also my start will be. This would be very nice, because then we have more time for the accelerated class. And I have booked rooms for extra hours of the accelerated education on Wednesdays, because you told me you are free every second Wednesday. So, the problem is that I asked, not me, but Professor Ratz, asked the dean, and the dean has a different imagination, ideas how to fix this problem. The core of the solution is I have to take unpaid leave and someone will replace me. Good luck for finding anyone to replace me. I told Professor Ratz, perhaps it's better if he does not find anyone. I will give you the course until end of March. I give you your homeworks, and then you will write the test and what is the name, the exam, I not test, the midterm exam and the exam with someone else. It is recorded, so I will not continue this, but we will sum up its issues. If I'm not here, good afternoon, then there will be a genocide. So this is not that part. So this, I have some pedagogical and teaching instincts, and I think this is not the way how you best understand the physics, how I teach it right now. So sorry. Okay? So, this Wednesday, there will be no extra class, except if I write you will advise. Okay. Where we are? Okay. The requirements. So, I don't expect you to be here, because to check whether you are here is extra work. You will have 3 homeworks, and 5 actually. It's obligatory to complete 3 and send me in time. Please. Then you will have a signature, and you also have to write and reach at least 40% of the points at the midterm exam. Then you will have a signature. Yes?
If you complete all 5 of the assigned homeworks, will there be extra points, or it's just...
Yes, I remember. Thank you for reminding me. I just wanted to tell you, if you do the exercise 4 and 5, you will get extra points, 10 points, 10 points. And if you pass, you have the signature, you pass in the exam, you have the minimum points, I will add. And from, I don't know, it's average, you will get excellent. It happened. I like to give you good grades. So I'm originally a researcher, so I give lectures for MSc and PhD students, not BSc. And there are some secret agreement that all midterm Fs, the average of all midterm text here must be between E and the B, but I never heard it or saw it in Britain, so it's a joke actually. Yes, this is the extra credit. Yes, and what you have to do, you have to pass the midterm exam and the written exam. The written exam is just 10 questions for 5 points, and you have to answer. You will see, I will provide you the solution. The solution is very simple. This lecture, this slide. This lecture, this slide. I will not ask anything else that is on the slides. Okay?
Thanks so much. Thank you.
I think that's the minimum. It's not a pleasure to make you done the exam again and again. Someone has, I don't know, it's this hobby, not me. Okay, these are the thresholds. I think they are quite good. Well, I can tell you. You can read the Feynman, but you can use the internet, you can ask me, and you can also use AI. I just discovered something. I use ChatGPT, and I have to recognize that there is AI in Google, and also I use this Hungarian mobile company, Takom, and its chat has AI, and also the messenger has AI. It's very good because, for example, I use it to improve the English of my slides. Okay, where we are. You are professional in normal mechanics now, Newton laws and everything. And I told you during your training some kinematic stuff. And now you will be professional in rigid bodies. But because we are very quick, we can also talk about oscillations. Oscillations are great. Well, I have 40 slides for today. There is something that I regretted. So before rigid bodies, I explain you again the Kepler laws. You know there are Newton laws, there are the laws of robotics, and there are Kepler laws, for example, laws of thermodynamics and everything else. The Kepler laws are important because I'm working an astronomer. So what was the point? From the observation of Tycho Brahe, Johannes Kepler, from a lot of observation, understood how the solar system is working. The planets, small bodies, comets, everything, are orbiting in ecliptic orbit around the Sun. And the Sun is one focus point of the eclipse. Do you know what is an eclipse?
The full circle.
Sorry?
Like the full circle.
Full circle, yes. What is circle?
I mean, not circle, the full like range of motion, or like, I'm not sure how to.
No, the geometrical definition. What is the geometrical definition of eclipse? No eclipse, sorry. Ellipsoids.
That has two focal points.
Yes. And
edges.
Yes, and?
It's a collection of points
Yes.
or that are the same distance from two focal points. I mean, whose distance, the sum of their distance is the same to the two focal points.
You mean that this distance and this distance do you mean this?
I think yes.
Yes. So the circle is the collection of those points which distance from the center are the same. In 2 dimension that's a circle, in 3 dimension it's a sorry? Sphere, thank you, and it continues to 4 dimension. When I was in secondary school, I did the codes how to project 4-dimensional cubes and circles to 3 dimension. Doesn't matter, it's not important. Ellipse means the collection of points which distance from the 2 focal points are the same. Do you know what is hyperbola? Hyperbola? This is not Kepler laws, I just want to tell you something. You have 2 focal points, 2, and you find those points which distance from these focal points, the difference of the distance from these focal points are the same. And this gives Wait. I think I'm not wrong if I write this. This could be very different. Yes, parabola, paraboloid, parabola.
Yeah.
Do you know what is it? What is it? Collection of points that.
Like a bowl, kind of curvy bowl.
Yeah. You have a line, and you have a focal point, and the parabola is the collection of points that has the same distance from the line and the focal point. Okay. Why I am talking about this? First of all, because it's interesting. Second, we will learn something related to this, and I don't want to tell you than this one. These are very interesting objects. The ellipsoid is interesting because of the Kepler laws. Ellipsis. The hyperbola is interesting because you can make a mirror. And you have this mirror, and the so you have the mirror, and if you have any light, then it focuses to the focal points. You can do telescopes in this way. Also, with this one, if you do this something metal here, then if light comes, then it crosses and reflected through the focal point. So you can do telescopes. You can do the same with spheres, but then there is a problem. The screen, you have a star, this is your viewpoint, and the stars has twisted coma with spherical mirror. But the hyperboloid and the paraboloid does not have. If you have a cup of tea or coffee, and you spin it with a spoon and left it, then the surface can be calculated, it's a paraboloid. So when they made huge astronomical mirrors, 10 meters diameter, then they put the glass in a rotating place and let it not froze, not melt, so just become rigid, solid. They need months to do it, and then they don't need to polish the surface. Even if you have mercury, and you rotate it, and it's a big mercury, then you have a very good mirror, but it can only observe on the zenith, but still very good. If you have this ellipsoid in space, you can stand here. If this is in space, and if you say something, then the voice will focus in this point. Have you had this experience? I have a program for you for 1 weekend. Just I don't know in English. It's close to the beach youth. It's so slow. Okay, this is in Hungarian right now, but English. Science Center. It is oh, it is not there. It moved. Moved somewhere else. Okay, there is this Csopa, Csodák Palotája Science Center. I suggest you to go there for a half day and enjoy the experiments and everything. It will improve your physics skills. It's really interesting. You can see a lot of things. Optics, mirror, waves, oscillation, whatever you want. But it moved. It was close to the other campus of this university. It's weird. But I have something else with this, because this type of mirror, was used in a historical moment. Ladies, do you wear bikini? Do you have bikini? Dress, swimming dress. Do you have? Do you know where the name comes?
From the Bikini Atoll in the Pacific
Yes.
Ocean.
And what happened at that Bikini Atoll?
Atomic nuclear experiments, US United States.
Yes. And do you know anything particular about this experiment? Yes?
The first hydrogen bomb.
Yes. And what else? That's okay. That's the common knowledge. I know a little bit more. It's thermonuclear. You could have uranium or plutonium, and you can split the atom. That's fission. That's simple, relatively simple. That bombs were thrown for Nagasaki and Hiroshima. For the hydrogen bomb, it's thermonuclear. You put together hydrogen nucleus atoms, the core, and then it forms helium, like in the sun, and you have a much larger explosion. The problem is that you need a traditional fission bomb to initiate the fusion. And now it is different, but at the very first time, at the Bikini Atoll, they used a heavy shell it was something heavy. In one focus there was a nuclear explosion and everything was focused to the other, and this was the fission, and this was the fusion. So this is how they used the ellipsoid mirrors for not only waves but for explosions. But there was something that they didn't advertise. The hydrogen comes from lithium. Actually, lithium 7, that's an isotope. It has 3 protons and 4 neutrons in the core. If you have the lithium, there is something else. Lithium 8, 3 protons, 5 neutrons. They thought that it will not react in this explosion. They was wrong. So the beginning first experiment was 50% stronger than they expected. So they put the cameras, the sensors and everything, and they were vaporized. So it was a successful experiment, but it was too big. So they had to do it again because they had no data, because everything was deleted, vaporized in much larger radiant than they expected. And they finally fixed the problem that they removed this isotope and there was only lithium 7 isotope for this. That's the story of the bikini atoll and everything. And now you know more about the mirrors. But what is important, that the Kepler laws. So the first Kepler law is that all planets are orbiting around the sun in an elliptical orbit, and in one focus is the sun. That's the first law. The second one you have this eclipse, and Kepler constructed a special radius that is delta P, and this is the radius from the planet, from the sun to the planet. It has an area, and this area is the same. What does it mean? A planet travels and orbiting faster when it is closer to the sun, and orbiting slower when it is further in the sun. Okay, for example, you can see in the comets, when they are very close to the sun, then they glow very, very fast, and then when they are beyond the orbit of the Neptune or further, then it's
their tail disappears.
Not the tail disappears, but they are slower. They're moving slower. And also there is something which close to this one. Just I need the exact formula. Where is it? This one. So the third law you have the sun, you have one ellipsoid, it has axis, this is major, this is minor axis, and you have another planet, and you have different minor axes and different major axes. The Kepler law says the what does it mean? The orbital period of the Earth is 365 days. And one astronomical unit is the distance from the Sun, the average distance. The Venus has something 240 days, and the average distance from the Sun is 0.7 EU astronomical unit. The Mercury has something 80 days, and its the distance is 0.4 astronomical unit. The Mars has 2.2 astronomical unit distance, and 1 year is something 600 or 700 days. The Jupiter is even has a longer period, and there is the Neptune. The Neptune has something 200 years, not days. It was so much time, but Kepler and the Kepler laws need some respect. Newton was a genius because from dynamical laws he deducted these laws, everything. And also he invested the mathematical analysis that is necessary for the calculations. In the time when most of the people could not read or write and starved to death. And many people just collected fruits in Americas or Africa or something like this. So these laws are historical. It's not only physics, it's part of the culture. And this is very important, and I did not explain you properly last time, which is a shame. Okay. But also a shame that I wasted so much time for this. So I have 40 minutes right now, if I understand well. 40? When is the end of? You understand? Huh? 3 o'clock? When is the end of the?
1 hour.
1 hour. I have 1 hour still. Great. Okay, sorry. This will be very, very fast. Too fast. We will talk about rigid bodies. Everything that I told you last time was about mass points. And I even did not define what is a point mass. A point like object with mass, and this object, blah, blah, blah. I have this. If I do physics with it, then I don't interested in the shape or everything. I replace this with a point, a mathematical point, which continues all the mass. That's a mass point. It's okay? It is written nicely what is here. You know what is mass?
Yeah.
That's great. Because, well, it's difficult. In particle physics, all interactions are transferred by particle exchange, and only recently find the appropriate particle for the gravitational force. You know what is inertial mass, and there is gravitational mass. Doesn't matter. You know what is mass. I think I also have some point about this or picture. System of point masses. Not everything is a point. This is larger. Or, for example, if you go back to the Kepler laws, if you consider the Sun and, for example, the Earth, these are system of points, 2 points. If you have 3 points or 9, that's much more difficult. Do you know the science fiction at Netflix free body problem? You never seen?
I heard about it.
Read it, Netflix, you know Netflix. Actually, this is a 4-body problem. I could tell you a lot of things about this. I have a full classes, a full semester about 2-body problems, perturbated 2-body problems, 3-body problems. The motion became very quickly chaotic. You cannot predict the future, but still you can do something. It's very, very interesting. I cannot tell you about this because we have to pass. Have to not pass, continue, carry on. Okay. Collection of multiple point masses referred to system of point masses. This mouse, my glass, this cover, or anything, set of points. There are some other things that I have to explain. There are forces that act in this system of point masses. There are 3 forces. 3 forces, you can change the action point, and you can also change the shifted parallelly. That's a free point. Semi-free force, free force. If you can change the action point along, for example, a line, and if you cannot do these things, then it's constraint forces. I will show you examples during the practice. You have external and internal forces. If Sorry. Carousel, great. Haha, yeah, I should have known it from. No, not that one. I need. No, not exactly this one. This one, excellent. Here are these kids. If these kids are standing there, standing on the carousel, they can push to each other, they can throw, they can do anything. These forces are inner forces. Some systems, they have importance, some system, they doesn't have importance. Usually we neglect them, and there is this guy. He is an external force and accelerate this carousel. This is very hard because I don't know what do you know about physics. Okay, open system, closed system. We always use models, and these models very often arbitrary. For example, if I would have plenty of rubber balls here, and I would just throw to you this everything, then these balls would not leave this room. So this would be a closed system. But if I would check the air, how the air is working, then it passes the window and the door. So it's not a closed system. If I check the heat transfer through the doors or everything, it's also not closed. I can put some isolation and then it's an isolated glass. This is always arbitrary. We do not study and calculate with the reality. We have a model which is closed, and we arbitrarily put some features to make the calculations easier. If it can predict something, then it works. If not, we have to change the model. If I have the laws of Newton, I can calculate whether a building with such concrete basement and blocks and everything is standing, then the law, the method, the model is good. If I calculate it well, and there is no problem with the material, blah blah blah. So you must know the limitations. If will not stand, then something bad in the Newton laws, or you did not recognize something. For example, the basement is not on rock, like in Finland, but in a muddy place, or you built it in a permafrost and that's melting, and so on. I would speak more about this. Okay. I have this, and this object can spin and can do anything. If I am in the room, so the size of this is negligible to the size of the room, then I don't care about the shape. I will replace this with 1 point. I have a system of points, and I replace this system of points with 1 mass point. And in this great case, this is how you can do it. if you have only 2 points, then it's understandable how you do it. It's you just replace this out. This is the discrete stuff. But if you are in a larger body, for example, this one, and you have a lot of points, you can replace the discrete sums with integrals. You know very well the integrals are sums. There are Riemann sums and Riemann-Lebesgue sums. And in this point, if a mathematician would be here, should be in the head. But don't care, we are engineers and scientists, so because it's not accurate actually. But that will be fine right now. Rigid body, the object of this class, is solid body when there is no deformation. It's set of points, multiple mass points, but the distance will not change. Actually, this is not really how things goes, but in ideal case, that's fine. It has a center of mass. For example, the center of mass is the same like for the set of point mass. You replace the rigid body with the point which has the all mass. Actually, when you do the physics, then if there is a force and passes this center of mass, then it will not spin the body. And what else? If there are a lot of things. The humans has somewhere here, not fact, humans has somewhere here the center of mass. When I was a child, we did something like this. I cannot do it right now. We put the elbow and you can hold your body because the center of mass is somewhere here. I will not show you better. Okay, here that's the same, but you can see just with integrals. If I say that you lost the rope, the line, or do you understand? This is the same. So if you say see this one, this is here. And this is here. And if you replace the discrete points with continuous stuff, continuous matter, then this is the same, but the sum will change for integral. If you understand what is integral, then you understand this. It's not easy. Yeah. Fortunately, I had already students, thesis workers, and they know everything from all subjects. Just put them together, mathematics from this, physics from this, chemistry from this, observation technique from this, electronics from this, was too difficult to them. But they learned it. Okay, rigid body. for a rigid body, it is very, very important if you have a force where it is its influence line. If there is distance within the center of mass and the influence line, then you have not a force, but this torque. This is a rotational equivalence of the linear force, because for a mass point, that's simple. But if you have something, this is the center of mass, and the force is go there, that's fine. If the force has the influence line here, then there is a distance with this one, and it will accelerate this body, but also it start to spin, rotate. And also you have to calculate the rotation. It has historical reason. This was clear for the Greeks. They have different, very simple machines. But, okay. So this is this torque actually. And the common stuff when you have, I don't know, one children and you have other children, but with belly, it's M, and then the distance is the same, but this actually, you know this from primary school, actually. Just now we use vectors and vectorial multiplication. You know what is vectorial multiplication of vectors? You know scalar. There are three other ways how you can multiply two vectors. But it's not part of this class, unfortunately. Angular momentum. You know the momentum, it's mass multiplied velocity. Here, you don't have mass. You have just the mass for a mass point. But for example, you have this ellipsoid. It has one main semi-axis, two minor axis. No, it's not one, it's just C. It is important if you want to start a rotation, the shape. There are techniques how you can calculate this one. If you have a disk, Okay, there is nothing that I could use. If you have this disk and you try to spin it, if it's very large, it's heavy, then you need different force and torque if you want to rotate here around this axis, or you can do the rotation in the opposite axis. This is difficult. It's called tensor analysis, impulse momentum, matrix algebra. Matrices. You know, you have a rotation, you have other vector, and the relationship is not direct, so it's not, you cannot calculate the scalar. You need a matrix. If you want to learn this, you need the full semester actually, so this is not the best. So there is the momentum for mass point, and there is so-called angular momentum for rigid body. The velocity, it would be m here. Here, you have, instead of v, you have omega. This is the rotational speed. You have this momentum, and this is the impulse momentum, which is this momentum depends on the shape, and this is the angular momentum. Now a lot of things. It's a good task for integration or everything to calculate this moment and everything. Another. There is kinetic energy here. Okay, you know the criteria of a bad lecture. Do not write in formulas, do not explain them, cover them, and erase the table before you can write it down. So, you have the kinetic energy, it's mass and the square of the velocity, and there is a half constant on it. The similar stuff for rotation. Also, there is a rotational energy. The constant is the same, but you have the inertia here and the angular velocity is the same. And actually, with integration and everything, I could calculate it for you and deduct, and perhaps you would understand what is it. Also, you have other stuff, conservation laws, angular momentum. It's if something is rotates, then it remains rotated if there is no external force. This is angular momentum. If you are on this carousel, there was a typical game that you are in the carousel, you take it, you put your butt otherwise, and someone spin it, and then you go closer to the axis, then you accelerate. The angular momentum will be the same, just because you change the geometry and the inertia will be different, but it will be lower when you go closer to the axis, but the angular speed accelerates. Mechanical energy, if you have this energy, it will also not change. In theoretical mechanics, there is something that called Lagrange formalism, and if you check the infinitesimal change in space, in time, in angle, you can deduct these conservation laws. So if someone says, I made the perpetuum mobile, then he's an idiot, because writing perpetuum mobile deny the conservation of energy, and the conservation of energy is deducted from the different laws of the universe in any time. It's difficult, it doesn't matter. Actually, Szilárd Zsóka did the same. He tried to explain things that it's too much. Okay. Usually, when there is a motion, there is a translation motion and a rotation. I try to explain you this one. And when you have any task with it, then you have to calculate the linear momentum, angular momentum, and the kinetic energy. And the kinetic energy, you have the kinetic energy and also the rotational energy. Okay. This was the rigid bodies. 2 full lectures. 2 full topics in the syllabus. Then I had a teacher in secondary school, and he always asked that from joke. No one understand? We can carry on. Actually, now that's the case, I think, because I see your eyes. Perhaps in the practice I can help on this. Then, harmonic oscillator. This is very, very important, and they told me I have to explain you, because you will see a lot of, plenty of, doesn't matter, plenty of oscillation as electrical engineer. Those oscillations will be, of course, not mechanical, but something, no, it's not possible, okay, doesn't matter, but something electrical, but you must understand the concept of sorry, what is the problem? Too noisy, or you understand the concept of oscillations. Last time it was winter, now it's autumn, so it's fine. Wait. Okay. The harmonic oscillation is quite important, not because it is only an oscillation, but if I do rotation, it looks rotation. If I change, I'm looking for you because you are in the middle, do the same. You see one component. This is a unique rotation with a unique rotational speed, sorry, that's opposite. But if you remember trigonometry, then this is phi, then this is cosinus phi, and this one is sinus phi. We could toy and play with it, but if you understand the rotation, then the result of an oscillation is one projection of this one. What it does mean? You have spring. You have mass on the spring. And why spring is important? Because the force is proportional to the dislocation from the equilibrium point. It has answer G, that's the gravitational force, this is the displacement, and there is D times X, 0. And if you do replacement, then this and this will be proportional, the force which try to push it back and push it back, will be proportional, will with the displacement. You have this. I just give you the kinematic explanation of this. You have the Newton law. The Newton law says that the body's acceleration is mass multiplied. It's from the force. The force here is proportional with the displacement. The second temporal derivative of the displacement is the acceleration. Not that spring. Better. When I try to rotate my arms, I try to reproduce this one. There is a circular motion, and one projection is the wave motion. And in time, that's the oscillation. I will send you the link, okay? Here. That music.
There's two key issues of that.
Okay, it's English, doesn't matter. This is what I tried to explain you last time. There is this spring, and the force what occurs is proportional to the displacement. And this explains you how the velocity and the acceleration will happen. I should start with it actually. I will send the link to you. There will be more videos, just I didn't plan these videos. If you have the Newton law here, second law, you have this says this A is dx second temporal derivative. The displacement is proportional with this one. You got this form, and the solution of this second order differential equation, blah 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 blah. Where is it? This one sinus and cosinus is the same like that you have seen at the circle. And this equation will show up in quantum mechanics, in electrodynamics, many places. So that's why I should have take time, 2 classes, for example, and explain you. But it's impossible with this syllabus. If you don't understand, the problem is not in your side. And I will not ask in the exam to deduct this one. Because to deduct this one, I would need 2 hours right now. When I was young, I was faster. Then I would need a half hour. But still, it's not ethic to ask this one. There is a very important case. In electronics, it's very, very important. The damped harmonic oscillator. See, you have a spring, displace it, and you have a harmonic oscillation. The damp means there is something which dissipates the energy, and in this case, something is in the water. After plenty of calculation, you got this one, what you expect. There is this blue, that's the harmonic oscillation, and the red is the damped harmonic oscillation. The energy dissipates, so the amplitude of this oscillation decreases. Of course, you know what is amplitude, but I haven't give you the definition. So this is what you got. This is very often you can get this if you have a pendulum, if you have an electric device, you can see the same wave. There is a special case, harmonic oscillator, beat. It means there are 2 harmonic oscillators, same amplitude and phase, but the frequency is different, differs. You can fix the differential equation and you get this one. The next one in the last few minutes is very important. But I have to return because I missed this, something that called resonance. Do you know what is resonance?
Yeah.
So what is resonance?
Just going back and forth in a certain amount of time.
Yes. There is one oscillation, and there is another oscillation, almost the same frequency. Then the amplitude can reach incredible size. For example, you start an engine and has a self either resonance of the chassis, the structure of the car. And the engine accelerates, and once reach that axis, then it try to dump or take apart because the amplitude of the original oscillation increases. That's resonance. And because I will put this because I missed from this one. Oh, that's better. It's the return for this one. I will need this other stuff. Oh, it's different. No, where we are? That's okay. I will need this one. I just stop this. I need again something. Resonance. So what you could see, there are these forks, and if the frequency is the same, then they interact each other and the amplitude of the second one increases. There is a very special case. Do you know who is Theodor from Kalman or Todor, Kalman Todor? Yes? No, it's not this one. That's horrible. Okay. 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 There was a long bridge. It had an eigen frequency, and yes, it is somewhere in the nature. Here. There is an island, and the wind flows from one direction. Vortex will appear on one side of the island, and later on the other side. One side, other side. That's why you see this vortex new line. At this Tacoma Bridge, the wind blowed, and Kalman vortexes appeared and left the bridge, one side, other side. And once this vortex leaves, then just shake the bridge. And the frequency of the creation of these vortexes was the same like the eigenfrequency of the bridge. So when the weather was windy, they experienced big amplitudes. And one day, it was not storm, just a strong wind. It was not just one direction. The amplitudes became big and it collapsed. That's a resonance. Okay, I have 3 minutes, but I have to finish this one. You are an engineer, and you must know the 4 fundamental operations. It's not adding, multiplying, dividing, and subtracting. No, it's derivation, integration, Fourier, and Laplace transformation. Now, you will understand the Fourier transformation. Not really, but at least you will have some idea what is it. Does anyone has a rock band or play piano or synthesizer? No? Do you know what is a synthesizer? You push the button, and sometimes piano, sometimes organ, sometimes it's a violin. Why? Because you can put all form of waves from sinus and cosinus waves. Actually, these are a different form, but doesn't matter. If you have an appropriate tool, mathematical tool, you can, for example, do a square wave from sinus and cosinus. And this is what I prepared. There is this real maths with. I will send you the link. No. Here. It is on Instagram, so it's not TikTok, it's Reels. But it's good. Where we are here. There is a. This is the Valentin knob special. But this is Fourier series that I would like to explain you. Music? Zack, zack. It's very small, but these circles, this one, there is one circle, and it gives only a sinus. You cannot read this. You cannot read this, but you will be able to read on the screen. If you add more circles, actually more sinus harmonics, then you got this shape of waves. If you continue this, you will reach the almost perfect square wave. This is composition. So with you can analyze the square wave, and you will get a set of a sum of sinus waves, oscillations with different amplitudes. This operation called Fourier transformation. But you can do the opposite. You could have waves and put together these waves, and you can get this square wave, or anything else. I will send you, and it's, for example, this is, no, it doesn't matter, it's not good. The Valentine times, no, it's not good also. Doesn't matter, this Fourier is good. And now, it was supposed to explain you with these slides, actually. You have a time series, ft, and with certain operation, you can break it into, it's a periodic time series. You can take it apart to sinusoid waves. This is the Fourier theorem, this is the Fourier analysis, and this is how the Fourier sets looks like. What is it? Cosinus. In the cosinus you have an amplitude, you have an angular velocity or angular something, you have rotational speed, you have time, it has an amplitude, it has a zero amplitude, and the cosinus and the sinus also have this one. This A, 0, A, K, B, K are the Fourier coefficient. The method is to determine these coefficients. And with these coefficients, you can put together oscillations, sinusoid oscillations, for example, to a square sign. It is very important in electronics. The method is the same, like in mechanics and everything. I don't know whether you are expert of the improprious integral right now. Yeah, I learned this in the second semester too, 30 years ago, and I didn't understand so much. Doesn't matter. Check this mapping motion. So, there are a lot of things that I skip right now. I taught at the University of Page linear algebra and advanced linear algebra in the fall and the spring semester. And at the end of the spring semester, after 1 year, we reached the Fourier transformation that you got right now. This is an operation when you will forced to use it, then use a tool, a Python library or something like this. You can do a lot of interesting things with it. You will learn what is convolution or anything. You will know what is frequency spectra. Do you know what is frequency spectra? Not yet. Doesn't matter. It's okay. you can use always this Fourier transformation. So there is this Fourier transformation when you have a waveform that's periodic and you get the sinusoid waves with different coefficients that results that causes the original waves, or you have inverse Fourier transformation when you have the oscillations and put together a special waveform that you want to design. That's necessary. Sometimes you need square, sometimes you need something triangulum, doesn't matter. You will use it in electronics. And this works. There are two different ways when you have discrete, when you use sums, and when you use integrals for continuous signals. Actually, all signal, everything, all measurements is discrete. The continuous stuff is in mathematics and in theory. And okay, last slide, sorry for the extra 5 minutes. If you have non-periodic signals, you also can do the same Fourier transformation. Okay, your fat line, your brain is cooked. Sorry, and this is the end of the lecture. Let's keep a few minutes break, and I will continue with the practice. Thank you very much. Could you please stop that one? Thank you.